Hi and welcome to another MoTeC webinar. My name's Pete Swinney and this is part 4 of our Introduction to M1 Diesel Tuning. This webinar is about some of the things you need to get right on the engine with calibrations, things like that, before you start your tuning. And we're going to finish the webinar today with the making sure you've got your head around the injector timing considerations, what affects injector timing, what an injector timing curve should look like, because it's something quite different from ignition timing on a petrol engine. Alright, so to get started with, we've got to have the right sensors on our engine and the right calibrations. This sounds quite simple, but one of the first things that you come across as being a little different on a diesel is the fuel pressure. So the fuel rail pressure is very critical to the fuel strategy inside a diesel engine, and the reason for that is because we have a huge variation in fuel pressure. So a significant amount of our fuel is delivered proportional to the fuel pressure going up and down. So I mean, just to pick some numbers, 50% of the fuel's delivery is via making the pulse width larger and smaller, or longer and shorter, and then say half of the fuel delivered to the engine comes from lifting the fuel pressure up and down. So it's a significant part of tuning a diesel. So we need to make sure that we've got the correct calibration for the pressure sensor, which is on the common rail. Okay, so assuming you've got that right, the next sensor to be worried about is the boost pressure sensor. Now the reason I mention this is because it's very common to be lifting boost pressure a long way outside the range of the factory sensor. So the factory ECU might, or the factory engine might be, say, running 14 pound or 1 bar of boost, 1.2 bar of boost. The your version or your tune-up might end up running 2 bar, 3 bar, or 4, or even 5 bar of boost. It's quite easy to do in a diesel to double the boost and double the power. So there's no point in setting off on our tuning and having a boost pressure sensor that's going to run out. So you should consider that straight away and fit something like a 5 bar map sensor, or certainly something that's appropriate to the boost levels that you think you're going to run with. If you haven't done this particular engine before and we haven't got you a start file for the engine, then measuring the OEM version of it is a good idea if you can. So try and find an engine that's standard in a standard vehicle and do some measurements either with an OBD2 diagnostic tool, something just to give you an idea of what the factory range is, and we'll talk a little bit more about using that tool later as well for other things. Alright, and the next thing to consider is the mass flow meter. So if the boost's going up, you can imagine the whole idea of the boost going up is for the airflow to go up. And hopefully you've taken on the fact that the best way of actually measuring the air going into the engine is to use the factory mass flow meter if it's going to be big enough, or some other version of it. So if we are going to be producing significantly more power than the factory rating, then the chances are that the factory fitted airflow meter is not going to be big enough. So it's a good idea to either fit a larger airflow meter, such as the one pictured in front of you there, that's and one from Edelbrock. So if you can find an airflow meter that's larger and you have a calibration for it, then fit that and get the calibration installed into the ECU. You can actually remove the air mass meter element out of the factory housing, so you can remove this element out on a lot of airflow meters and then fit or make a larger diameter housing and then fit the element into that and then scale the calibration appropriately. So as much as we'd like you to have an accurate calibration, it's at least I'd rather you had at least a calibration that gives you something that's repeatable, even if it's not dead accurate. So put as much effort in as you can to get the calibration as accurate as possible. And then while we're talking about EMS meters, some of you the flash tuners amongst you will know that even changing airflow going out of the meter or coming into the meter will actually affect the calibration. So you can have an airflow meter that's calibrated perfectly in one particular installation, and you can put that into another installation where the pipe and duct work is significantly different, and then it can actually change the calibration numbers required for accuracy. So sadly, that's the world we live in with MS meters, but try and put as much effort as you can into getting that as accurate as you can, because that will pay off in getting the fuel model, or what the ECU calculates the lambda to be, as accurate as possible. And again, just going to talk about the injector calibrations. So again, as much effort as you can into getting those as accurate as possible. So currently getting them individually calibrated is the best way forward, or going with a single, or getting one calibrated from a diesel calibration shop, or anyone that services port injector diesels will be able to do some sort of calibration for you, or talk to your MoTeC dealer about how to obtain good injector calibration. So that's important. Again, just covering it off, the most important part about the injector calibrations is if you're after very good pilot control, where we're dividing up small pulses or small volumes of fuel at idle into 3 pulses. If we don't have very, very accurate injector calibrations down at those lower flow rates, then it's difficult for the ECU to divide off those very, very small milligram amounts. So take from this screen, what I want you to do is get the calibrations on that mass airflow and those injectors as good as you possibly can before you even hit the dyno, and that would be the best way forward. Alright, so some starting points for tuning. So it's nice to load in some known or some start values. One of the critical ones is fuel pressure and injection timing. And as you'll learn, injection timing is not that easy to predict, because it really is interlocked with fuel pressure. So the higher the fuel pressure, the shorter the pulse width can be, and the pulse width is what determines effectively where the injection point should start. So if we have a very long pulse width, then we need to start that pulse width earlier in the cycle so it doesn't burn too late down the exhaust side. So I've got a graph coming up to show you that again. Alright, so we need to consider that. But most of the time the fuel pressure curves are reasonably standard, as far as they can be similar amongst a lot of engines, as far as high fuel pressure at high loads and lower fuel pressure at lower loads. Now, just a note on fuel pressures that isn't to do with power, and that's to do with the fact that the intention from OEMs is to have fuel pressure coming, or fuel coming from the injector nozzle, and at a pressure that pushes the fuel out through the multiple holes and fills up this piston bowl area here. So in an ideal world, that bowl area here would be completely filled with a nice mist of diesel and air, and then once it gets, once it lights off, it's got good distribution around the combustion chamber. So the OEs try not to have the fuel blasting into the side of the piston wall, because that can cause erosion and cracking and things. So they want fuel pressure to be high enough to fill the area, but not so high as to be, do a water blasting effect. So what a good starting point is to try and find out, roughly what the OEM has intended the fuel pressure to be on that engine at each given operating point. And a way of doing that, again, is an easy way of doing that, is if you can get onto a standard vehicle and use the OBD diagnostic tool and have a look and see, and you can do some sort of recording of what fuel pressures are at any given flow rates, boosts, engine speeds, things like that. Alright, so you just need to come up with some sort of a base an idea of what the manufacturer was intending, and then put your own take on what you're going to do with it as well. Alright, so having considered all of that, the higher the fuel pressure you can run in general, the better. So the higher the fuel pressure, the better the atomization, and the better the fuel reaches all the different corners of the combustion chamber. Now there's a couple of limitations. So if we run excessively high fuel pressure at very low fuel requirements, then we end up with a very short a short pulse width. And so if our fuel pressure is so high at, say, idle, that our pulse width to deliver the correct amount of fuel becomes too short, then it can go underneath what the dead time of the injector is. So to give you an idea, we might have 10 microliters being requested to be delivered at a fuel pressure of 96. So at 96 MPa at 10 microliters, our fuel delivery is 0.429. If we come down to 2 microliters, we see to get 2 microliters, which is almost nothing, it takes 0.315 of a millisecond, or 315 microseconds, for the injector to deliver 2 microliters. So what that gives you an idea of what is the dead time of the injector. So we don't want our pulse widths to be much less than this lot of numbers for this example. Alright, so and you'll note that as we go up in fuel pressure here, our dead time is actually decreasing, which is the opposite of a port fuel injector. So what that is inside the injector design, the increasing fuel pressure actually helps to open the pintle against the spring. So it actually helps to lift the pintle out of the hole, I suppose, of the nozzle, and that means the higher the fuel pressure, the faster it opens. So all our injector linearization tables should all have a similar shape. Alright, so as the demand for fuel increases, so that's across our horizontal axis, we should see the number going up. And as the fuel pressure increases from, say, 16 MPa, which is quite low, and heads up to 180 MPa in this case, we should see those numbers going down. Alright, so you'll see the shape roughly something like what you see on the screen here now. Alright, so one other thing I want to mention while we're in this table is if you don't have good injector calibrations, and that is unfortunately something that you're going to have to deal with as tuners in these early years, until we get on top of an automatic way of doing this. You can, as a tuner, fill these tables out and make them better. So you can, if you have a very accurate airflow measurement coming in via an accurate airflow meter calibration, and if you have an error in your lambda estimate versus your actual lambda, then, and you're confident that the airflow measurement is correct, then the error that you see in the lambda estimate is coming from this table, from the fuel calculation table. Alright, so you can actually update these tables yourself and try and bring what the ECU thinks the lambda is to match what the actual lambda is. So now the reason I'm bringing all that to your attention is that if you don't have this table accurate and you have a fuel pressure control problem, then you can have a situation where, for example, at this particular site here, if the engine was running delivering 31 microliters of fuel and at 144 MPa, and we had a fuel pressure control issue, and the fuel pressure dropped to 48 MPa, which is a significant drop. If these numbers aren't correct on this vertical axis, or the whole shape of this table isn't correct, then the lambda will change significantly, and that changes the power. So the amount of fuel that gets delivered to the engine will change dramatically. Now, you might say, yeah, that happens in a petrol as well, but to a far lesser effect. So if the fuel pressure is moving around on a petrol between 5 bar and 4 bar, the actual volume change isn't that significant. Now, yes, it may lean out a little bit if you haven't got fuel pressure measured, but it won't change the engine's power much at all on a petrol. But on a diesel, if you don't have this linearization table accurate and the fuel pressure moves away from where you've tuned it, then you can expect a significant change in power. Now, depending on which way you've got the number wrong, power can go down, and that's safe for smoke if you're worried about some smoke, because it'll lean out. But if you've got this number too big down the bottom, then the power can increase. If you're trying to run to a smoke rule for racing, something like that, then that could be enough to cost you a drive-through or something like that. So hopefully you've gotten it on board that this is just a critical table that you can't really spend enough time in updating and making sure it's right. It just makes everything in your tuning life with diesels easier when you have unexpected problems. Alright, so basically this page just goes further into that exact scenario. I kind of jumped ahead on you there. So that's the scenario again, just showing you that if your fuel pressure does fall for whatever reason, if you hit a fuel pressure relief valve and it stays stuck open, that's pretty much exactly what will happen. If the fuel pressure spikes when, say, the driver lets his foot off the pedal, because the demand for fuel goes to almost nothing on overrun, and the pump or the fuel system doesn't have a bleed back to the tank, then it's common to get an overspike in fuel pressure. Now you have a relief valve for that, and on the old mechanical relief valve systems, the relief valve can sometimes jam open, and you end up with a scenario where you're running around the track at a very low fuel pressure compared to what you tuned it. Alright, so just a little bit of tuning tips on setting your fuel pressure table up and how to tune fuel pressure, closed loop fuel pressure on a diesel. So this is a pretty typical curve on the right hand side of what a fuel pressure aim map would look like. Starting down the bottom, we've got our fuel flow, and actually I think our latest software, it is fuel flow estimate, maybe fuel mass. Oh no, that's right, the fuel flow estimate's on the feed forward table. So this is your fuel mass going on the vertical axis, and as you demand more fuel, you can demand more fuel pressure. Why do we want more fuel pressure? As we want more fuel so that we can keep our pulse widths as short as possible. Why do we want our pulse width short? Because if we have a very long pulse width and we're still delivering fuel and we're after top dead center, and then we can have fuel still burning, going well down the exhaust stroke, or well down the power cycle I should say at least, and that can give you boost control problems, and obviously you don't make a lot of power by having late injection, and you can have smoke problems. So we want to keep our pulse as short as possible. As the pulse increases, we increase our injector timing, but you get to a point where if the injector timing is too far advanced, you build too much cylinder pressure on pre top dead center, and you can damage the engine. So there's only so much advance you can put on your injector timing. So the rule as a starting point is to try and keep that fuel pulse, that injector pulse width, as short as possible, and having high fuel pressure is a way of doing that. Alright, so as soon as we've got any engine speed and any particular decent amount of fuel demand going to the engine, we want to increase our fuel pressure. So the highest numbers we've seen on the diesels we've worked on is something like 220 is the highest pressure that we've seen manufacturers run on the Isuzus, and sometimes not that high on other brands. So start conservative here. If the maximum pressure allowed is 200, then start kind of a bit under that until you get your fuel pressure under control, because while you're tuning your fuel pressure control, you'll see big spikes over, and we don't want to hit the relief valve if we can avoid it. Alright, so that kind of shape and those kind of numbers, if you don't know what the manufacturer ran from factory, try and again go to the OBD2 and have a look and see what the normal engine is running on the factory vehicle. You can ask us and see if we know what it is, or we might have a start file for it. So in the 186, 185, 190, somewhere around there is pretty typical for today as being a top number. But as I say, as you get the fuel pressure under control, you'll find that the advantages of running more fuel pressure, if you can, once you can come closer to the maximum pressure allowed, creep up on that as you get your fuel pressure control better and the actual fuel pressure itself smoother. Alright, so that's the kind of shape we want to go with, and as a starting point. And then, like all other closed loop control systems in M1 or M800 for that matter, we have a PID algorithm to control, in this case, fuel pressure, and the starting point for that PID is a feed forward table. In this particular case with fuel pressure control, this is very critical to get this right, and so that's why I've highlighted it in red and asterisked it. So the numbers here, because most of the suction control valves, which is that duty cycle valve on the end of the pump that the ECU controls, most of those valves don't tend to have a lot of duty cycle range to change the fuel pressure dramatically. So even changing these numbers by 1 or 2 can make quite a big difference to how good the actual fuel pressure control will be. So again, this is a little bit like your injector calibrations, where you keep coming back to this feed forward control, or the feed forward table for the fuel pressure control. And on the vertical axis of that, you have your fuel flow estimate, primary being the primary fuel, in this case diesel. So as the fuel flow goes up, the feed forward numbers will need to change to make sure we deliver the correct amount of fuel to match the aim. Now we'll do this in a later webinar. We'll do this live and you'll see the process, but effectively as the engine is running, you will see the integral, which is the time element out of the PID control algorithms, fixing the error. So if we had an error of 4 MPa, the integral component will fix that up, and then it might end up with something like 2 or 3 or 4 or 5%. So you then, as you're running the engine, you can alter these numbers so that you remove the integral component out of the control. So if it had 5% positive integral, that means it's had to add 5% more to these numbers here wherever it's running, and then you can basically highlight the numbers and just keep either paging up or add 5% to make sure that that integral component is reduced as close as possible to 0. You want a situation where that no matter where the engine is running in its different zones, load points, etc., that we want to see that the feed forward number and the actual control number are as close as possible. That'll give you good fuel pressure control and just save you that grief of engine surge and things like that coming if the fuel pressure control is bad. Alright, so again we'll do this live, and a few more of these tips will come into play, or you'll understand a little bit more. Just a final thing, you can, as a worst case scenario, filter that final pressure channel to help the lambda, because what we're doing here, or what we're risking, is if our fuel pressure control is erratic, then we can have an erratic lambda occurring, because in the real world very accurate injector calibrations are difficult. Alright, so last screen for today, injection timing. And the idea of this is to keep hammering home that key difference between a petrol and an engine and a diesel engine, being that we're only injecting the fuel at that last moment in time, and that fuel as that's being injected determines when it lights. It's not determined by the spark, it's determined by when you put that fuel in. So it's not how most people would think. And so we've got the two graphs which you've already seen in an earlier webinar, and the first one showing how we've got a 0.8 millisecond pulse width here, so 800 microsecond pulse width, and we have our cylinder pressure trace happening just before top dead center. Now simply by adding extra fuel to make more power, so you want to put, the driver puts his foot down and adds power. If we leave our injection start point at that same location, we effectively retard the cylinder pressure. You're retarding that fuel delivery because the pulse is going longer to add the fuel. So, and that is in the case where you're not adding fuel pressure. So if we don't add fuel pressure and we just add pulse width to deliver our extra fuel, so if we put our foot down and we go back to our fuel pressure aim, and if we don't add more fuel pressure, then the only way more fuel goes into the engine is that the pulse has to get longer. Okay, so just want you to understand that as pulses increase, then the combustion moves to the right. Your effective 50% burn point, or your peak cylinder pressure, moves to the right, and it's just the same as retarding the ignition timing. So if we add pulse width, then, and we want to keep our combustion pressure in the same physical location in the cycle, then we need to move the injection timing to the left. So we need to start the injection timing earlier. So more pulse width equals normally more timing, all right, which is not like a petrol engine at all. Now obviously if we've got a fuel pressure aim set so that as we ask for more fuel we get more fuel pressure, then the effect of the pulse width lengthening won't be as much. It won't lengthen as much. And so what tends to happen in the real world is that first, let's say half of the power that you ask for, maybe even the first 2/3 of the power that you ask for, can be delivered by and simply increasing fuel pressure. And so the pulse width doesn't have to change at all. You can actually design the fuel pressure curve so that the pulse width can just remain the same. Now from that point on, as you add more boost and demand more fuel, if the fuel pressure is already at its maximum, then the only way to put more fuel in is to open the injector for longer, and in those cases then the cylinder pressure is moving to the right. So from somewhere around 3/4 of factory power, you'll find that the pulse widths will start lengthening, and it's quite common to see a pulse width somewhere around 2 to maybe even 2.5 milliseconds, which is a really long time in diesel world, and to make, you know, something like 20 or 30% more power than the factory system. Alright, as we keep adding more and more fuel, if our fuel pressure is already high and we can't go any higher in the fuel pressure, and if we keep adding pulse width in this direction, then the only way to stop the combustion being too retarded is to keep adding, or to keep adding injection timing, so to move this pulse to the left. Alright, but again, as covered earlier, the risk with certainly high boost engines when you start delivering fuel too early is that you can achieve cylinder pressure that's so high because the fuel is lighting before the piston has even reached top dead center, so we're getting cylinder burn occurring and the piston's still well down the bore, and so we can get very high cylinder pressures occurring, and then we risk a situation of damaging the engine. So we commonly see numbers somewhere around between 25 and 35 degrees before top dead center as an injection timing point, with boost levels somewhere around 40 psi on say a 3-litre diesel engine. They're the kind of maximum injector timing numbers that you'll see. And as you can imagine, our maximum injector timing actually happens at higher engine speeds and at higher fuel demands. So the injection timing graph is almost the exact opposite of a petrol. With a petrol, we retard the ignition timing as boost and fuel load demand goes up because we're worried about detonation. With a diesel, we're actually adding injector timing to try and get that fuel burned or injected and that start point for the fuel to be burning, so that we end up with a 50% burn point somewhere around 10 degrees after top dead center. Alright, so that's the aim. That's the general overview of how you might think about doing your injection timing numbers. And if I put that in terms of you've got your engine on the dyno, yes, you can just move the injection timing around until you reach peak torque. But if the fuel delivery time is long, as you get longer and longer and longer, the burn is going for so long, it's happening a long way before top dead center, and the burning is still happening a long way after top dead center. You will see with your torque increase for every amount of extra fuel you put in that you'll get less and less torque, because you have to keep adding more and more injector timing, and you almost get to a point of no return where you don't get anything. Alright, so how do we fix that? The best way to fix it is to run larger injectors. The problem with that is, in a diesel, each manufacturer kind of has an individual injector designed for that particular engine, so it's not that easy to just go and find some larger injectors and bang them in. So what we've discovered, at least, is that there have been manufacturers out there designing larger nozzles. Basically, they make a replacement nozzle to go on the end of the injector, effectively with a larger hole in it, and that delivers more fuel. But like most things in the world, there's always a compromise. So often there is delivery problems at idle, just like larger injectors in petrol, smoking problems. So there's definitely good and bad nozzles out there, and it's something you should be aware of. And of course, if we change our nozzle when changing our fuel flow, we have to start again with our injector calibrations. Alright, so that's the skinny on injector timing. Hopefully that's reasonably well understood, and keep it in the back of your mind as you're looking to produce your power, that too much timing can do damage, but you need to add timing to make the power to keep the combustion in the right area. Thanks for listening. We'll be back with the next part soon, and we'll catch you then. See ya.